Hi, everyone. Happy Tuesday. Thank you for joining us for today's presentation. I'm going to wait a few seconds here to let everyone enter in from the waiting room. And I know some people will join in the next few minutes here. But the presentation today that we have is with Linda from Hohmann Barnard, and it is designing durable and thermally efficient facades with stainless steel rain screens attachment systems. So a few things about today's presentation. It is AIA approved. So if you haven't already submitted your registration number, feel free to do so. I'll drop a link in the chat once we get started with the presentation. That's to ensure you receive credit for today's presentation. Second thing, any questions you have, please drop them in the Q&A. We'll have a few minutes at the end. You can also chat them to me as well. And then the last thing, we'll be launching a webinar poll about 3/4 of the way through the presentation. It is a really great way to connect with Linda and the Hohmann Barnard team after today's presentation in regards to price quotes, product literature, samples, any project specific support. And I'm going to quickly share my screen. And this is where you'll be able to find Hohmann and Barnard's brand page on Acelab. This will be that second link I'll include in the chat. Got really great information here about their products, including cut sheets, certifications, things like that. And then scrolling to the very bottom, some really great case studies. This is a really great place to go if you would like to organically connect with Hohmann and Barnard. The last thing I'll share, and this is pretty important for the end of the year here, is a way to connect with many of our manufacturers, including Hohmann and Barnard. I'll drop this link in the chat, and this is a really great way to request things like lunch and learns and in-person office presentations, as well as virtually, so you can get those CEU courses before the end of the year. Okay, I'm going to stop sharing my screen. That was a lot of information. You'll see a few links in the chat from me. Please let me know if you have any questions. And I'll let Linda take it away.
Is it still showing my seminar then?
It is.
Fantastic. Okay, let's get started. We have a good number of you on. As a recap, my name is Linda Potter. I manage our architectural team across Canada and the US. I have, 20 years now in commercial construction and working in this way of working with architects. And so there's a little bit I've learned along the way, and I hope I can share at least something with you that maybe is new or you don't know, or maybe just reinforces maybe something you thought was true and where we're at. So let's get started here. We do have our seminar. I'll do this AIA page. This is an HSW as well. So I know those are coveted learning units. The description's kind of long-winded, but it's part of those things we have to put in to get these things approved. What we're really going to get at is these modern high performance facades and how attachment systems impact what you're trying to do for energy code, things you have to think about for balancing energy efficiency, durability, flexibility. We'll talk specific about stainless steel clip-in rails, but also talk about a few other things that really impact the overall building envelope to which you are always trying to build and work through. So I am going to do a case study specifics. I think we can learn a lot from looking at specific details and specific situations instead of just the generality that these sometimes can be in education. So our objectives, we're going to talk about critical roles Rainscreen attachment systems play. We'll compare materials of stainless steel into others that exist in the market. We'll talk about thermal bridging and maybe talk about some things that might challenge maybe the way you're used to thinking about things. And then we're going to work through that case study. I can't talk about Rainscreen in any way, though, without mentioning the Rainscreen Association in North America. Now, we know that by RAINA. It started in 2020, and it is a place that if you are designing Rainscreen wall assemblies in any way, that you should bookmark and go to, because it has so much information. And it's built by not only product manufacturers like myself that are in there, but it's also your most highly coveted facade consultants. It is your structural engineers. It is your architects. It is folks of all types of materials that exist in a Rainscreen assembly that have worked together to come together to, one, define what a Rainscreen wall is, but also other definitions and work to getting things into code. Because as you probably know, there isn't anything in the code at this point that tells you how to design these rain screen walls. And so you're utilizing your own experiences, probably leaning on some of the most technical people in your organization or previous experience you've had, but there's still so much we don't know because there's still so many new innovative products along the line. We have to ask ourselves, how does all of this work together in a way that we can trust is going to give us the long-term performance of a building that we expect to have? And so part of what came out of RAINA was just that, defining what a rain screen is. And so this is what everyone debating inside of that room came up with. So it's an assembly, not materials, that are applied to an exterior wall, which includes an outer layer, an inner layer, and a cavity between, sufficient for the removal of passive and liquid water and water vapor. So what does that mean? That means that we're not talking about specific materials. We're not talking about whether something is open jointed that truly allows rain in for a rain screen wall. This can be a lot of different types of wall assemblies that fall into this rain screen wall. And what we're going to talk about and why this matters, I think we have to start here is by saying there are benefits to rain screen walls that are far beyond what other ways you build your buildings can be. And a lot of those are listed here. Moisture management, the ability for a rain screen wall to say water will likely find its way in, and we have designed a way for the water to get back out in a way that dries things out quickly by venting and ventilation and cavity space that improves the thermal performance of a building. And you get both air circulation and ventilation, but goodness sakes, you have an endless ability of aesthetics. You can choose from any cladding you want that building to look like and put those cladding materials in a way that functions as a rain screen wall. We can have reduced maintenance costs. We can speed the installation up potentially, depending on how big of a panel you're going to put in. We increase the number of people who can install these claddings. We have potential optimal use for recladding buildings. We just came from the Rainscreen Association in North America, their annual conference, and we heard 3 case studies of recladding that have happened and what some of these architects went through and how these things worked and how that impacted the actual occupant comfort and the energy efficiency of these buildings, in addition to increasing aesthetics and making them perform better. There's a lot of things that we can do here that we need to talk through why we want to know more about rain screen walls. And the biggest issue is because we are trying to eliminate this type of thing from happening, the consequences of water. So we know, again, walls let water in unless they're a perfect barrier that does not. So think glazing, maybe some different ways that water's never going to get in, or you don't intend it to get in because there isn't a way for it to get back out. That's a different topic. But so this is a case study in the Pacific Northwest. Again, this comes from RAINA as a case study that they work through in one of their seminars. But this is a project in the Pacific Northwest, and it's a project that did not have proper airspace. So it did not have the ventilation, and it did not have the drying capacities, that wetting drying impact. And so materials stayed wet, and then they became problems. And this is a big issue for your occupant owners of saying there is a huge cost to having to restore buildings because they didn't get built in a way that allowed them to be sustainable and durable, and they needed to fix them because of this simple thing of air gap and ability for it to dry and ventilate. So other potential consequences of not getting these things right, potentially cladding detaching from the building. We saw projects last week where, movement is one of the biggest things that you'll deal with. And the fact that your backing moves different than your cladding moves, and we have to allow for that movement, or panels can push up against each other and cause cracking and then make those fall and detach from the building. Sometimes it's that we don't manage the weight of that. And then the weight just literally comes off of the building. Not something you want to have happen. You potentially run into air barrier failures. I've learned in previous seminars or conferences rather from RAINA where they talked about the fact that it was an open rain screen cladding. Okay, so we allow constant UV because there happened to be in a part of the country that didn't require continuous insulation. And so the air barrier had permanent UV exposure on it, and no one thought about that. And so the air barrier that went in failed. And as such, all of the cladding had to come off and the air barrier had to go back on, the appropriate air barrier. You don't always think about those things, but you've got to think in assemblies, not in individual materials. And the problem that you run into so frequently is that you might put together a wall assembly on your plans that you know works, but then in the VE process of everyone coming in and the different trades and the different scopes, things get swapped out, and we might look at compatibility, but you might not look at it from different angles. And so this is just this moment for us to say, gosh, do I think about the air barrier when I think about my Rainscreen walls, depending on what that's going to receive for exposure? You potentially have to think about putting these systems together for NFP 285 requirements. Maybe we're thinking about the risk of fire and smoke, of combustible claddings and combustible materials throughout that assembly, and what that means for your project. So if we get back to the basics of Rainscreen wall components and we look at it from the Rainscreen perspective, this is our cladding, airspace, backup structure. This is something you're probably very familiar with, a very basic detail, and it really mimics this masonry cavity wall. I have to go from there because that is my background. Most of my background is in masonry walls. However, from a RAINA definition, a masonry cavity wall is a Rainscreen wall still. So we have to, I think it just helps us keep in mind how all these components come together. Even if it's not brick as the cladding, we're still thinking about it in the same way. So we've got this brick, we've got the airspace, anchors keeping the brick on the wall, the insulation, the air barrier, and the structural backing. So when you think about this cladding layer, though, if we're thinking about it in just this holistic idea of what a Rainscreen cladding can be, it is your first layer for water control. So if you have a brick wall or a stone wall in front with mortar on it, you have very little water intrusion coming through from the face of that. Unlike if you use a panel with open joints that allows a lot of water through. Those are different of how they're going to shed that water, and as such need to be designed as such because both are allowed in terms of what a Rainscreen wall is. That type of material an option of joint impacts that water penetration. You have to think about at this layer also combustibility. Am I choosing a material that is combustible or not? And it doesn't matter because a lot of materials will work, but you do have to think about them in terms of systems so that you pair the rest of the components up accordingly to how you need these things to perform in terms of corrosion, durability, the air gaps, all those kinds of things, depending on how that cladding might absorb moisture, might dictate how you put the rest of that wall together. When it comes to this airspace gap, in the masonry industry, we have always known 2 inches to be what we really prefer. But we didn't know if that was because that's the mortar reason. So then you're stacking bricks and you've got the mortar that smushes out behind to go down the wall cavity. We thought we needed 2 inches to stop the mortar bridging, but also mason's fingers have to go into there. So you kind of have this like 2 inch of what we settled on, 1 inch minimum in order for that mortar bridging, but it wasn't necessarily because of ventilation and the drainage purposes. So what Raina went further in is said, and we looked at several things, and you can find this on the Raina's website, is that about 3/4 of an inch is the optimal of an air gap to get the most ventilation, the most drainage potential for those systems to function. Because you also have to think about anything greater than that, potentially 1 inch and greater, might also trigger some NFP 285 or some of those chimney effects in some of that fire that you've got to think about. You're thinking about fire stopping, you're thinking about airflow. But what we do know is most commonly we want that to be that air gap, we want it to be, if possible, right behind your cladding layer. So what's the backup structure? It can be anything, really anything. And Raina walks through this as well. Wood framing, steel frame with exterior insulation. We've got concrete CMU walls with exterior insulation. We've got ICF, cast in place concrete, precast concrete, unconditioned wall spaces. There's a lot of things that work here. And so then it's saying, okay, those 3 things are the bare minimum of what it requires for you to have a Rainscreen wall. But there's more components, right? We can't hang a cladding out there and expect it not to be connected back to your structure. So we have cladding attachments that go part of this assembly. It's what we're going to focus a lot of time on today, but we know there's just as much importance in the rest of these components. So you've got your insulation. There's a lot of different types of insulation on the market today. They all have different attributes that you've got to think about depending on how you're going to design and what that means for your building. You've got your air barrier for air tightness and the vapor barrier for that vapor diffusion of the wetting and drying control layer. So let's kind of dive deeper a little bit in cladding attachments then. Here's the things you're thinking about likely when it comes to cladding attachments, or I hope that I inspire you to care about it just a little bit, because I think a lot of times it gets forgotten. And we think that the installer or the cladding facade manufacturer that we specify is going to control what this attachment is. And that might be true. And it also might not be true. And so I really want to encourage you to own this into your scope as a design member, of trying to say, I need to care about what this is. This is what is going to connect to the back structure that's going to hold the weight of the panels of the facade of whatever that's going to be. So it's going to be your cladding connection. It's got to handle the capacity of what you're putting on that. It is your thermal bridge layer. And so we do have to think about maybe the conductivity of material, but I also think we need to think about this, how frequently that we're placing these. We have to think about combustion. Is that layer combustible or not? Because there's options that are, and there's options that aren't. Again, all work, but you have to think about what requirements you have with energy code and different owners' requirements. There's a lot of things you're thinking about. Most at the end of the day, you've got to think about the durability. Can it handle the facade that's going to get attached to it? When it comes to what you're thinking about insulation, you're thinking about the combustibility, right? Is this a layer that's going to trigger? What's the thermal value? So we know that there's installations out there that aren't combustible, but they have poor thermal values. So you're going to need more of that. Or I can switch and I can change and I have a thinner layer, but maybe I have to worry about some of my fire, types of NFP 285 assemblies and approved, and look at all of those assemblies along the way. You've got UV resistance again. So think about this. You've got, if you've got something open jointed, that insulation could potentially have permanent UV exposure. How does it handle it? Can it handle it? Most importantly, I think, is just that we know that it should be located tight against that backup for its maximal thermal performance. So it must stay tight against that backing for it to give you what you should for optimal assemblies. That if we get to the design requirement or the design performance standards of which we want it to perform as, it's only going to do that if it stays where it's supposed to stay and is tight against there. Here's your air barrier. You cannot talk thermal in any way if you don't talk about the air barrier. That air leakage is the biggest offender for your air leakage. Almost up to 40% of that energy cost to heat and cool a building is due to air leakage. If we stop the air, we stop the water. If we stop the air, we increase thermal performance. Your vapor barrier matters just as much. It controls that water vapor by vapor diffusion. So the thing that we see a lot out there, because as you're putting these walls together, some materials are vapor barriers in themselves. Your air barrier may not be your vapor barrier, or it may be. But you have to think about the entire components inside of there of where you're going to put this vapor barrier and how it's going to impact the adjacent materials around it based on where we're stopping that vapor. We really know that the high performance buildings have the ability to keep something, to allow something to be wet and dry them out quickly. That is what we're talking about in terms of that vapor barrier. So what are our Rainscreen challenges then? There's a lot of them, right? I think some of the biggest ones is that it's ever changing. And your energy codes, performance standards are ever changing. And if your firm does work across the US, those codes and standards are different. I want to just remind us that those codes are the minimum for you to design to. And that means that you can do better if you know better, even if your code doesn't mean that you have to. Now, I know your owners control budget. And there's more, it's so much easier said than done. But I just think it's important that we just stop for a moment and say, energy code drives so much of why we're doing things different. And it's also because we've learned that if we don't put codes in, that failures happen and then building code gets stricter. And this will never stop, the cycle of it. So you've got challenges putting Rainscreen walls together because you have to think about thermal bridging. And there's a lot of ways to look at that. You mostly have to be worried about air tightness. Now, air tightness comes back into those energy codes. You've got complex detailing because you've got changes in facade panels. You may have brick transitioning to metal panel. You might have stucco transitioning to metal panels. You definitely have windows and doors. You might have storefront connecting to panels. You've got complex facades now because it's rare that we just select one material and build an entire building out of it. So we've got to put those materials together and think about movement and think about how the building envelope stays continuous yet allows for these different facades to work together, because maybe we have vertical facades paired with horizontal facades, and it's lovely design and presents you more challenges in terms of detailing so that it stays beautiful 10, 20, 30 years from now and doesn't end up with cracks and failures along the way. You've got that facade failures that comes next is the potential for these things to not be designed and detailed correctly that gives you issues, whether that's water or detaching cladding or you name it along the way. There's a lot of things that you maybe have run into that you could add to that list. But those are the things that we have to work through, and where the basis of what we're talking about today hopefully takes you to think about this maybe in a different way. At the end of the day, the bottom line on code is this, at least this is how my brain likes to work through what we deal with at code. The IECC sets your minimum compliance baseline. ASHRAE 90.1 tells you how to quantify those losses. And Passive House, which we're doing a lot now, depending on what part of the country you're in, Passive House pushes for the near elimination of those losses by pretty much air tightness and reducing your thermal bridging to near minimum if possible. Now, we know we have to have thermal bridging. We've got to keep a structure on first. Before we can care about the energy and the thermal bridging, you have to keep people safe. You have to keep the buildings intact. Facades can't be falling off of buildings first and foremost, and then we worry about the energy side, but structure has to dictate. Just ask your structural engineer, they will tell you that. Okay, so we do have attachments, we know that they have to be included. Those thermal bridges are included in your modeling when it comes down to your whole assembly and where that fits for your energy code. But you're not going to get any of it right. That thermal bridging doesn't matter at all, in my opinion, if you can't get your air barrier right. If you continue to have gaps and holes and poor transitions and just bigger, like, you have to care about the air barrier. If we do that right, the rest of this is minimal. But if this doesn't get done right, I don't care how much you stop thermal bridging of your cladding back to your structure, it's never going to give your owner back what you told them it would in energy savings, or in terms of some of you are in code climates that your owners are going to get fined by using too much energy, and it's all because of this air barrier layer. And so this, I have my sweet daughter's picture here just to remind us of the winter coat theory. You can have all the insulation, you can have the windbreaker layers, you can have everything that you need in here. And if there's a hole or a tear and air can go right through it, it's still going to be cold. It doesn't matter how much insulation is in that coat. If you allow the air to get through, it will still be cold. And so I think it's just important that if we don't get this part right, why do we even care about the rest of it? And so the importance of detailing with air barriers is all in the continuity. It is not necessarily just those big opaque walls that are real easy to get right. It's the transitions, it's the openings, it's the ductworks, the utilities, the anchor penetrations or the clip penetrations potentially, the angles. We've learned so much about how stopping thermal bridges actually does more for the air barrier install than maybe it even does for the thermal bridging impact. Take shelf angles, for instance, in masonry. The way we used to do these is really big linear lines that have so much thermal transfer that the insulation doesn't even matter because, we're completely giving it back in this area. but it went on before you ever put air barrier on the building. So the ability to get that air barrier continuous was really challenging, where offset brackets allowed you to do the air barrier first, then attach your angles that were offset that allowed insulation back behind and got you a full system that now makes sense. So there's changes in design that happen along the way that help us do things better, but it all comes back to that air barrier. How do we do that better? How do we put importance on that? How do we get out there and see it on a building before it gets completely cladded in? It's the part that has to be mattered about. And then we can care about the thermal impact of Rainscreen connections. I'm going to take you through a very fast study because I think it's how I demonstrate what stainless steel is thermally efficiently. So in the masonry anchor world, we took at the time with Morrison Hirschfield this barreled single penetration anchor, but it was a carbon steel zinc barrel. And we put it through insulation values of 1 inch up to 4 inch and spacing up to 8 inch to 24 inches. And we looked at and tried to understand what did it do to the effective R value of the building. Now, at 1 inch, at 16 inch, because that's the typical masonry spacing, we still were at 90% of effective R value, even with the anchor penetrating through. Not bad. If you go up to 4 inches, you're down to 81%. And still, code does not recognize this as impacting your R value. They are still clear field anomalies, I think is what they call them. And they are small, but they are numerous, and that they don't really impact things. But we know they do, because anytime you interrupt insulation, it impacts your R value. But when we take that same study and we change just that same barrel from zinc to stainless steel, you're already at 92.6% with the 4 inches of insulation and at the 1 inch. So we know that most of your masonry wall assemblies probably have 2 to 4 inches of continuous insulation. If not, I've seen up to 8 and 10 inches. And so the more insulation you have, the more this matters of ensuring that you have something that's not going to impact or take away from that effective R value of that insulation. So what we know about stainless steel is that it is thermally efficient. It's durable, it's strong, it does not have corrosion problems, it is fire resistant. And now we add this thermally efficient to it, and we start to look at something in the industry and say, maybe I don't have to have a completely non-conductive material as my subframing. Maybe I can use stainless steel and make my structural engineers happy while still giving me the thermal values back that I need for energy code. Because we, in our studies of this, we found that stainless steel brackets can retain that effective R value of up to 96%. Now that is based on spacing and optimized spacing. That will not happen on every project because there's other factors that dictate spacing of clips. But what we want to show here is that there is potential, and we can design things in ways that help them stay that way while giving you something that is thermally efficient, fire resistant, corrosion resistant, strong, durable, something you can trust and rely on. But we also put it with an aluminum rail. Now, so the stainless steel connection is your structure back, is your clip back to your structure. That's the majority of your thermal bridging, yes? I can't make the rail stainless because I have flexibility that's needed. I have in and out of my installers because the structure is rarely straight. So you've got to have the flexibility of pulling those in and out, and you can't drill through stainless steel very easy. So it stays aluminum as the rail so that you've got the flexibility for installation purposes. Because you know what? If we're making these buildings so complex with detailing, you have to keep in mind the folks installing it. You've got to keep it as simple as possible. If we keep things simple, they tend to install it correctly. When it gets installed correctly, your buildings tend to work. That's my very simple philosophy of these buildings. There's a lot of ways you can do things. Some have to be near perfect for them to work out the way they're intended and tested for. Some allow you to do almost right and still give you great results because of belt and suspenders approaches. So I think just, there's a little inside knowledge of how I feel. But so you've also probably heard, we don't put dissimilar metals together. That's a complete, nope, we don't do that. So what do? We had to do a big test on this. We had to get rid of the potential of the concerns of mixing metals. And so we put it through a 1,500 hour salt spray testing. And this is what it looked like before. This is what it looked after. There's things to note. There's always a something that is because of that. So this is using type 304 stainless steel, and it's using 5052 or 6000 series aluminum. Now that is key because it is very high quality aluminum that we are putting in connection with the stainless steel. And the caveat, the thing you cannot forget, is the fasteners of the aluminum into the stainless steel must be stainless steel. They cannot be carbon steel and think you're not going to have some corrosion along the way. So that is why engineering is so important, or that we look at the details of saying all of this is great. We just can't forget the fasteners. Sometimes I think we forget about fasteners, but they control so much of these projects. So what about the conductivity of material? The thermal bridging is something that I think, we constantly look at material first, and I think that we should, because it tells a big story. If you look at this here, you start to see the progression of maybe where we've gone because of code reasons along the way. So we start with this continuous vertical Z-girt. It's the worst offender, right? This is a study from RDH. And then you look at the continuous horizontal girts, and they're still bad because you've got the continuous linear bridges of thermal bridging. Then you go to clips. You've got an aluminum clip, which is highly conductive. Then you've got your galvanized steel clips that are better. Stainless steel clips that show clearly perform even better. You've got some isolated galvanized clips. Then you've got your fiberglass clips, which are not conductive, but the fasteners are, right? Then you've got galvanized steel screws. So we're not doing clips, we're just doing fasteners. That's even better. Stainless steel screws, fiberglass clips, no through screws are going to be your best option, right? However, you can't just look at this and then holistically adopt, I cannot allow metal on my buildings for connections because they're thermal bridges. And if I just use fiberglass, then I'm safe, because you have more to worry about, right? First of all, you have to think about the number of times you penetrate your insulation, but also what? Your air barrier. The more times you penetrate your air barrier, the more potential you have for leakage, which is your biggest issue when you think about really controlling thermal efficiency and energy cost. So I'm thinking about the size of penetrations, potentially, the conductivity of material, absolutely. I'm thinking about how thick that insulation is to determine how much that might impact things. But I'm always thinking about the continuity of insulation. The less times I interrupt it, the better. And so it doesn't always tell the full story, because I can run an analysis of a project-specific situation where maybe I have fiberglass clips, but I have them at small spacing, and I compare it to a galvanized or a stainless steel clip, and I have optimized bigger spaces because of spanning ability, and maybe the stainless steel or the metal could perform better than the fiberglass. It just depends. So I think it's just important that we simply maybe consult what we maybe believe to be true, and know that there are a lot of ways I can put these buildings together. And so if I do have the need for something that is metal, that's non-corrosive, that's that stainless steel, I'm not giving up my thermal aspect of my project. It's just going to look different potentially. I think there's also this statement, I think that we think that there is this, a minimum things must be thermally broken. I think that we've told that story for a long time, but there's this also, there are building facade consultants that will tell you that potentially adding a thermal shim behind a metal or stainless steel clip, the displacement of the insulation, you can kind of see it visually demonstrated here, potentially is worse for the overall project energy cost than what the give back of the thermal reducer would be. Now, some people say it's really optics. My client wants to see it. The energy, the building code officials want to see a thermal break. I get all of this. But really, when it comes down to it, it's potential that just the clip to the backing is all that is needed, and may potentially even perform better than having a shim behind it that's thermally reducing shim. So we know that stainless steel brackets themselves can meet passive house requirements without a thermal break as well. And I'll kind of go through that here. Now, passive house is obviously, it's all assemblies. It's all per project. I get all of that. But we did find, and we worked through some modeling with a 32 by 50 inch clip spacing of a stainless steel bracket, we were able to meet the loads, because that's first and foremost structure first, right? But also the thermal results were what we needed in order to have passive house certification for those clips without the thermal break. And so we know it's possible. Now, 32 by 50 spacing, how realistic is that? Maybe it depends. And I think that's where you have to always know how to call and work with people that can work through that to determine if it makes sense on your project or not, because it might not. It might require certain things that impact your cladding in a way that you don't want to do, or the entire system that might add cost. And maybe that's not what we want to do. But I just think it's important that we just simply say, just because we are looking for passive house doesn't mean I can't use stainless steel. This is where I think it all comes down to saying, just like in stone anchors, those are not part of code. Rainscreen does not have code, which means that we really do need to engineer these systems all of the time. And so if your specifications don't call out for that, I think that we should. I think we should have an entire section that's dedicated to the sub framing of Rainscreen, and for you to vet based on your firm and the way that you build and the places that you build and the types of clients that you work for, the typical wall sections, and give them your options, because installers will just take, I love them. We need them. A lot of them are great, but you can't always dictate who gets to be on your job. And a lot of times we spend so much time, if you do, going through all of what we just talked about, these design considerations, only for a contractor to change it on you. And so I think it's just important. A lot of people are going to delegated design now because there's so much to consider. And if you have this subframing section that tells them these are the ones that we have vetted that we will accept, and give options, have fiberglass, have stainless steel, have some of your other types of metals. Look at all of it in terms of how it's going to impact your penetrations. Make sure that you trust manufacturers, and give some options to your installers to at least control them or keep them from doing something that's not thermally efficient, or that you don't want on your building because you understand air barriers in a different way than an installer would. We all have different perspectives. We all care about different things. I think it's just important that we continue to work through that. So your delegated design's thinking about wind loads, panels, weights, structure, substructures. They're thinking about fasteners. They're thinking about the structural components. They're thinking about the complex detailing. Well, maybe your delegated design partners aren't, but there's much to think about, from movement to weight to fasteners. Do you have wide cavity conditions? Do you have your facade transitions, your backup transitions? All of that is why engineering is imperative for you to have in some way, whether you've done the front end design work of that or whether you put it on your installer, that everything must be engineered with delegated design. I think that there is benefits to working with a manufacturer of doing delegated design, because they know how to design to their manufacturing capabilities to potentially do some VE work along the way. I think there's less potential for playing telephone, of too many people getting in the middle of all of this. You're working directly with people. They should be project specific design. They should have engineering calc, shop drawings, bracket and rail layouts. They should have part sheets. They can do in-house fabrication so that there's no miscommunication of how it gets engineered based on versus what they can actually produce. And I think that there should be technical support available for you along the way to do all of that. I'm going to wrap up these last, hopefully 10 to 15 minutes with this case study to show you in real time what that might mean for a project that you might have. So background on this is an 1.25 inch granite natural stone project. It's located down in Texas. The architect on this project wanted to minimize their thermal bridging. So they weren't going to use the typical way of how we install thin stone. So they specified a clip and rail Rainscreen system. There was all kinds of options. The difference here, and I think this is where we have to keep in mind the nuances of Rainscreen, because there is not one single trade that installs a Rainscreen facade. In this case, the mason contractor had the scope, and they would, because it was stone. Stone typically falls in the mason scope, right? So it just so happened that the mason got it, and the mason was familiar with us as a manufacturer, which is how we ended up with this project. Other people can get it and they would design it different. I think that's what's challenging too, is that when you start to understand there's a lot of ways this could be done, it's hard to detail without knowing specifically which system you're going to get. So it almost has to have loose hands with how you show detailing and almost look at performance requirements and standards of what you want it to do so that every manufacturer and installer that's working together can pair this in a way that works for the system in the most economical way. Or because masons, I'm sorry, just any trade in general, their labor plays a huge part of their cost. So if you start comparing cost of components, it really doesn't mean anything because contractors will assign potentially a different price to working with different materials based on maybe their experience, maybe their lack of experience, maybe how hard it is for them to work with. There's a lot of things that dictate end pricing. So when we allow multiple things in there, without just completely saying I can only have something that's fiberglass, you potentially eliminate some of these abilities for some VE opportunities. Okay, here's your case study. Back, let's say 20 years ago. This might be how we approach an 1.25 inch granite stone panel, where you might have this continuous 12 gauge horizontal C channel because we've got stud framing here, so that you had a framing where you needed an anchor to go back through. But you can see here, that's a huge disruption to the insulation. It's a huge thermal bridge. And so we moved away from that and said, hey, let's do a hi-hat. You've seen these in construction a long time. You still see these used on the outside of rails a lot of times. But typically we would put this straight back to the structure, right? So this would still give you linear bridges all the way across at top and bottom, but it would allow you to put insulation in between. Instead of the C channel, what's continuous, you now have a hi-hat channel that minimizes that disruption, but still is a disruption. And so when we introduce this clip and rail, you can see how it does perform more thermally efficient than your horizontal girts would, which is what we've seen in the RDH study along the way as well. So what you see here is a stainless steel bracket back to the structure. In this case, it's a CMU backup. And we've got a really wide Rainscreen. So it looks as though the insulation is likely 6 inches of insulation. And then we've got the ability for the airspace and then the cladding, the stone attaching to that. We've got thermal shims at the backup structure, and we've got thermal shims at the location of the connection of the stone to the aluminum as well. So we've got thermal breaks in both places on this specific job. What you'll see is that the stone anchor layout is where the outside facade is going to connect back to the rail. And what's interesting is that those attachments, I think this is why there's beauty to the subframing and the cladding connections to be of the same manufacturer if possible, because they can coordinate this layout. It can happen when you have different people doing it, but again, it just requires more meetings and more people's time in order to get it right. But you can see this anchor layout and the bracket rail layout. Now, the anchors of the cladding are attaching top and bottom of those brackets. I'm going to go back so you can see it. Look at the top. This is where our stone anchors are at. This is where the rail is. And so the closer that they put the fastening of the stone into the cladding, so it's attaching the stone cladding to where the rail itself was at, controlled deflection and allowed them to span further distances between those stainless steel brackets. Now, the stainless steel that you see here, that bracket it's a vertical rail that's connected 3 different times along that entire elevation. And so our spans are likely 4-foot spans of penetrations through. Now, the horizontal layout is based on a little bit more and has more coordination that, well, it doesn't have to hit stud framing, right? So we're able to kind of change those based on where the stone needed to be, and those coordination happened together. Now, our typical detailing was a 1/4 inch thermal shim at the CMU stainless steel bracket. It was a 12 gauge bracket that was 4 inches by 8 inches. Again, it was an 8 inch deep bracket to accommodate the 6 inches of insulation you can see here. And then there was a 3/16 aluminum that was 3 inches by 3 inches. Again, another 1/4 inch thermal shim if they needed it for the in and out adjustability. Then we had an 1/8 inch stone anchor. So that's the typical detailing. Here's what I really want to take away from this. A lot of your building will be typical, and a lot of it will not be. And so you need to be understanding the consequences of how we put these things together. Because look at this corner detailing. We've got typical corner. And if we go the other way, we see a jamb, which is a different detailing again. So if we lay into this a little bit further, we see here's what this wide cavity detail at the corner looked like on the plans. It's not specified, which is fine. It doesn't need to be because every manufacturer might look at this different. But what we looked at and we look at this and we say, we've got a simple building envelope because we don't have metal studs in here potentially to frame this out. We have less thermal bridging potentially because we don't have, but this is all just airspace. Nothing's in there, and you can fill it with insulation, but you still have to worry about keeping that corner condition where it needs to be. So we've got to add some structure. So then it looked like this. A thermal shim, again, that CMU stainless steel connection. But now instead of that 12 gauge stainless steel bracket, we've moved to a 1/4 inch thick stainless steel bracket that's 6 inches by 8 inches of a bent plate. And it's 3/16 third, it's still your same vertical rail. And still got a thermal shim there. But the fastener analysis is always included all of this. And it needed to be not this needed to just be a custom piece that figured out what those corner conditions would look like in order to manage the cladding support, the weight, the structural analysis. What happened at the jamb? Same kind of thing, where you've got this jamb. It's still another 1/4 inch stainless steel bent plate that's got to be there to manage what you've got for the gap because there's no structure here. Now, some instances you might see some framing laid out, and so that gap becomes less and you don't have as much on it. But if you're foregoing some of that miscellaneous or middle detailing in order to figure these things out, you can do it with stainless steel and put that on your delegated design, and they figure this part out for you. So I guess that in summary, a lot of this is that stainless steel Rainscreen attachments will handle the weight of any cladding, including your heavier stone. They'll also are thermally efficient. They meet passive house requirements without a thermal break. And they do resist that corrosion. They're fire resistant. There may be reasons why you want to look at that for your projects. Just knowing that at the end of it, you can do a lot of things. There's a lot of innovation materials out there, but it's how you put them together that determines whether or not it's going to work for long-term performance. So I think I made it in time. I see there's a poll up here. Do we have any questions that came through?
Yeah, there's two that came in through the chat, and I'm going to let everyone take a few more minutes to do the poll while we get through these questions, if that is good with everyone. Okay, the first one that came in, let me read this. It's a little bit, sorry if I missed this, but how much tolerance for movement and adjustment do your systems provide during installation, especially for larger format panels?
So I don't know that I have a specific answer for it because we can design it to be what it needs to be. There's a lot of customization there. So I don't have the standard, but maybe I do need to ask engineering if there is a limit, there's a maximum or a minimum to what that is. I just know that we have the ability to be adjustable and we can make it customized to what's needed to the project. I don't know if that helps, but there's my answer.
And anyone can always reach out to Linda, her contact information as well. Okay, the next one. Recommendations for mitigating moisture path created by Rainscreen bracket fasteners, penetrating air and water barriers.
So I do think it's something you have to think about. I don't have a detail where I show it, but I'm starting to think, again, I'm coming out of this RAINA conference and we are always learning all the time. So I do think there's potential that you're putting gasket tapes down over the top of those AVBs as an extra gasket sealing because those fasteners are going through and they may not go through perfect and they may get in there a little bit at an angle that may potentially allow for air leakage in there and with that water, right? And so I do think it's possible that like a 3-inch wide gasketing tape down those studs or down that mass wall may be in best practice of how you continue to do something that controls that.
Perfect. And then our last question here, feel free anyone to drop any more in the Q&A or message me through the chat. What thickness and grade of stainless steel do you typically recommend for different climate zones like Southern California, and how does this impact the system's thermal performance?
Yeah, I think that's a good question. We use type 304 always, and 12 gauge is our standard bracket currently. We have been asked if we can do something lighter. And if it was lighter because the panel was lighter, or potentially it didn't demand something as strong as that 12 gauge would be, can we? And we can do it. I just don't have thermal values of what that does, right, to impact it. We could maybe look at it project specific, but at this point, it's 12 gauge is what our standard is.
So that is everything in the Q&A. Everyone feel free to take the last few seconds to wrap up the webinar poll. You can also reach out through Linda directly here. Do you have any final notes or things you'd like to say, Linda?
No, thank you for your time. I hope that it was not a bore fest for you. I know that webinars can sometimes be challenging, so I appreciate your time and attention.
I thought it was very entertaining. Thank you so much.
Thank you. Have a good afternoon.
You too. Bye.
Bye-bye.